There was a time when gravity did not exist. This audiobook invites you to discover how one of the most fundamental forces of the universe was born, the one that keeps galaxies together and our feet on the Earth. Is gravity an inevitable property of space, or did it emerge at a specific moment in cosmic history? What we know and what we still ignore could forever change our view of the universe. Gravity is not just an abstract concept. It is the force that keeps us anchored to the Earth. Every time you jump, you feel its immediate pull, as if the ground is calling you back. But have you ever wondered how this affects everything around us? Gravity is the reason oceans have tides, why trees grow upwards, and why our hearts beat in perfect balance with the universe. When talking about gravity, it is impossible not to mention Isaac Newton, a giant in the world of science. His famous apple that fell to the ground not only inspired him to formulate the law of universal gravitation, but also opened the door to a new era of understanding. But why was his discovery so revolutionary? The answer is simple. Newton was able to describe gravity in terms that we could all understand, showing that this force is not just a whim of nature, but a principle that governs the cosmos. However, the story of gravity does not end with Newton. As we move forward in time, we encounter Albert Einstein, a man who dared to challenge established ideas. The theory of general relativity not only transformed our perception of gravity, but also taught us that space and time are intrinsically intertwined. But how can such a familiar force be part of something so extraordinary? It is fascinating to think that gravity is not just a force acting on large objects, it affects every particle in the universe. Imagine a fabric of space and time that folds and wrinkles as gravity acts upon it. This idea, although complex, helps us understand phenomena like black holes, those mysteries of the cosmos that challenge our understanding. But what happens inside a black hole? That question remains an enigma. Gravity also plays a crucial role in the functioning of our own solar system. Each planet, moon, and asteroid is in a cosmic dance, spinning and orbiting due to gravitational force. Have you ever wondered what life would be like on a planet with different gravity? Human experience would be profoundly altered. Imagine walking in a place where you weigh half or double what you weigh on Earth. Gravity affects not only our corporeality, but also the possibility of life on other worlds. As we explore beyond our planetary home, we find that gravity has even deeper implications for the structure of the universe. Galaxies form and evolve in response to the gravity acting between their components. Without this force, the universe as we know it would not exist. But what about dark energy, that mysterious phenomenon that seems to be accelerating the expansion of the universe? Gravity and dark energy are intertwined in a cosmic game that we are still trying to understand. In this journey of discovery, we cannot forget the role of science in validating our theories about gravity. Over the years, various experiments have tested our beliefs, from the simplest to the most complex. The fall of an object in a vacuum, for example, demonstrates that gravity acts uniformly regardless of the mass of the object. But what experiments are underway to study gravity in the context of quantum mechanics? The search for answers continues. Gravity also connects us with modern technology. Without its understanding, we would not have GPS or satellites, tools that have revolutionized our daily lives. But how is gravity related to the signals that allow our phones to work? The science behind these advances is a testament to the power of gravity and its influence on our daily lives. On Earth, gravity has been a crucial factor in the development of life. From the water flowing in rivers to the air we breathe, everything is shaped by this force. But how does gravity influence the possibility of life on other planets? The search for habitable worlds is underway, and gravity is a determining factor. There are many myths and misconceptions about gravity that have persisted over time. Some popular beliefs can lead us to misunderstand how this force works. Demystifying these concepts is not only important for education, but also helps us see the world with new eyes. As we look to the future, research on gravity remains an expanding field. New experiments and theories are constantly emerging, and each discovery brings us one step closer to understanding this fundamental phenomenon. Gravity, far from being a tired topic, is a field full of possibilities and mysteries to solve. Reflecting on gravity is also reflecting on our place in the universe. Every day, this force reminds us that we are interconnected with everything around us. From the moment a child throws a ball to the moment a galaxy forms, gravity is a constant that unites us in this vast and wonderful reality. So the next time you find yourself looking at the stars, remember that each one of them is there, in part thanks to the unparalleled force of gravity. The history of gravity is a fascinating journey through time, a path that takes us from the earliest observations of our ancestors to the complex theories that today attempt to unravel the mysteries of the universe. Who hasn't felt the curiosity to know why apples fall to the ground or why planets orbit around the sun? Since time immemorial, humanity has sought answers to these fundamental questions, and each discovery has been a step on the ladder of knowledge. In ancient times, civilizations like the Greek and Egyptian already speculated about the nature of gravity. Thinkers like Aristotle believed that objects were attracted to the center of the earth due to their nature. It was an intuitive but limited view. However, how did we move from these initial ideas to a deeper understanding? The answer takes us to the Renaissance, a period of renewal in scientific thought. The 17th century marked a crucial milestone when a young Isaac Newton formulated his ideas about gravity. But what led him to discover this invisible force that seems to govern everything around us? Newton observed how apples fell from trees and at the same time how the moon orbited the Earth. In his mind, both things were connected. In 1666, Newton proposed that there is a force that attracts objects to each other. And this idea would become the law of universal gravitation. Newton's law of universal gravitation was revolutionary. Imagine an invisible thread that connects all objects in the universe, a thread that tightens when two masses come closer. This idea not only changed physics, but also transformed our view of the universe. But what limitations did this law have? Despite its success, Newton's theory could not explain certain phenomena, such as the movement of Mercury or the light from stars that curves when passing near the sun. Thus, the need for a new theory arose. At the beginning of the 20th century, a brilliant physicist named Albert Einstein dared to challenge the established norms. With his theory of general relativity, Einstein offered a new way of viewing gravity, not as a force, but as a curvature of space and time. Have you ever thought of space as a fabric that folds under the weight of objects? Imagine placing a bowling ball on a trampoline. The fabric sinks, creating a depression that attracts smaller objects. This is essentially what Einstein proposed. Einstein's theory not only explained the phenomena that Newton's theory had left out, but also opened the door to a deeper understanding of the cosmos. Gravity, in his view, not only affects celestial bodies, but also influences time. Can you imagine that time does not flow uniformly everywhere in the proximity of a massive object like a black hole? Time slows down. That's an astonishing revelation. The theories of Newton and Einstein are not just ancient history. They are still applied in modern technology today, but the story of gravity does not end here. As we delve into the era of quantum physics, new questions arise. How does gravity relate to the forces that govern the subatomic world? This enigma has led scientists to investigate new theories and experiments. As we explore the history of gravity, it is impossible not to wonder, what does the future hold for us? Current research seeks to unite general relativity with quantum mechanics. Could there be a unified theory that explains all the forces of the universe? The idea that one day we might fully understand gravity remains a challenge for scientists around the world. The history of gravity is also marked by experiments that have validated the theories of Newton and Einstein. From Galileo's famous test of falling bodies to observations of light from stars that curves due to the sun's gravity, these experiments have been fundamental to our understanding. How many more things do we have left to discover? In summary, gravity has been a subject of study since ancient times and has evolved through key discoveries that have changed our perspective of the universe. From the early speculations of Aristotle to the complex theories of Einstein, The quest for knowledge about this fundamental force has been a constant in human history, and undoubtedly the story of gravity continues to be written, inviting us all to be part of this exciting scientific adventure. If you're enjoying this journey through the universe and want to keep exploring more cosmic mysteries, don't forget to subscribe to the channel and give the video a like. Thank you for being part of this Star Odyssey. The law of universal gravitation, formulated by Isaac Newton in 1696, is one of the fundamental bases of physics that helps us understand how bodies interact in the universe. But what does this law really mean? To understand it, let's think about two arbitrary objects like an apple and the Earth. When the apple falls to the ground, it's not just because of the force of gravity, but because of the mutual attraction that exists between them. Newton told us that this force of attraction depends on two things: the mass of the objects and the distance between them. The larger the objects, the stronger the force that attracts them, and the farther apart they are, the weaker that force becomes. Now, why is this law so important? Imagine if we had no explanation for the movement of planets or the fall of an object. It would be like trying to solve a puzzle without the right pieces. The law of universal gravitation provided humanity with a framework to understand celestial and terrestrial motion. It allowed us to predict the paths that planets and stars would take, and even helped us send spacecraft beyond our own planet. But it wasn't all that simple. Over time, the law of universal gravitation also revealed its limitations. How could a force act through the vacuum of space? This question troubled many scientists. While Newton's law was capable of describing many phenomena, it didn't explain everything. For example, as astronomers began to observe the movement of planets with greater precision, they realized that something didn't fit with Newton's predictions. Intriguing questions arose. What else could be influencing the gravity of celestial bodies? The answer came with the advent of Einstein's general relativity. This revolutionary theory, presented in 1915, completely changed our understanding of gravity. Einstein proposed that gravity is not simply a force, but a curvature in space-time created around massive objects. Think of a trampoline. If you place a bowling ball in the center, the trampoline will sag. Now, if you try to roll a marble near the bowling ball, the marble will follow a curved path toward the bowling ball thanks to the depression it created. This is how gravity works in a broader context. In this new framework, planets do not just orbit around the Sun due to an attractive force, but because they are following the straightest possible path in a space that is curved by the Sun's mass. This leads us to a fascinating question. If gravity is a manifestation of the curvature of space-time, how can we measure and observe it? The answer lies in the experiments that have validated the theory of gravity over the years. From Galileo's free-fall experiments to observations of Mercury's orbits, each discovery has added pieces to the puzzle of gravity. Newton's law of universal gravitation, while fundamental, is just a part of a much larger story. A clear example of this is the case of gravitational waves, which were predicted by Einstein and confirmed by recent observations. Can you imagine what it would be like to detect the waves produced by cataclysmic events in the universe, such as the merging of black holes? These waves are further proof that gravity is a phenomenon much more complex than initially thought. As we explore more about gravity, we encounter a new question. How does gravity relate to dark energy? That mysterious force that seems to be accelerating the expansion of the universe. Gravity, which essentially tends to attract, faces this force that seems to push. The interaction between the two is a hot topic in modern physics and could provide answers to many questions that remain unanswered. Still, Newton's law of universal gravitation remains an incredibly useful tool. It allows us to calculate satellite trajectories, predict eclipses, and understand the movements of celestial bodies with astonishing precision. Its legacy endures in the technology we use daily, from navigation systems to the design of space missions. However, the journey doesn't end here. The quest to unify gravity with quantum mechanics, the theory that describes the behavior of subatomic particles, is one of the greatest challenges facing contemporary physics. Can gravity, which seems so simple in its everyday manifestation, be reconciled with the strange rules of the quantum world? This question opens a new chapter in the history of gravity and invites us to continue exploring the mysteries of the universe. In summary, the law of universal gravitation was not only a milestone in science, but also laid the groundwork for a deeper understanding of reality. It has guided us through centuries of discoveries and led us to question our perception of the cosmos. Human curiosity about gravity does not stop here, and every new question that arises pushes us forward in the pursuit of knowledge. What new revelations does the future hold for our understanding of gravity and its role in the universe? Only time will tell. Gravity is a phenomenon that accompanies us at every moment of our lives, but have you ever stopped to think about how it integrates into the vast world of classical physics? To understand gravity in this context, we must go back in time and explore how scientists of the past incorporated it into their theories. Imagine a world where the forces governing the movement of objects were a mystery. For centuries, philosophers and thinkers questioned why things fall. From Aristotle, who believed that objects fall at different speeds depending on their weight, to Galileo, who conducted experiments with spheres of different masses, the search for answers never ceased. Galileo demonstrated that, in a vacuum, all objects fall at the same speed. But how did this fit into the puzzle of physics? The answer came with Isaac Newton in the 17th century. Newton not only wondered why objects fall, but he also dared to ask why the moon does not escape Earth's orbit. His curiosity led him to formulate the law of universal gravitation, which stated that all bodies attract each other with a force proportional to their masses and inversely proportional to the square of the distance between them. This was like discovering the recipe for a complex dish, a precise mix of ingredients that, when combined, reveals an extraordinary flavor. Newton's law not only changed the way we understand gravity, but also laid the groundwork for classical physics. In this new framework, gravity was not an isolated concept, but integrated with other forces and laws of motion. Imagine a game of dominoes. Each piece represents a law of physics, and gravity is the one that initiates the fall of the others. But what happens when conditions change, such as in the case of objects moving at speeds close to the speed of light, or in extremely strong gravitational fields? This is where the limitations of Newtonian physics begin to emerge. Although Newton was able to explain a great number of phenomena, his model could not address extreme situations, such as those found in deep space or the very nature of light. This led many scientists to wonder if there was something more to gravity that could not be explained with Newton's tools. In classical physics, gravity was understood as a force acting at a distance. But what does that really mean? Imagine throwing a ball into the air. At the moment the ball reaches its highest point and begins to fall, you are witnessing the gravitational force in action. However, for Newton, this force was like an invisible thread connecting the Earth to the ball, a connection that seemed magical. But the magic of gravity became more complex over time. As scientists continued to explore, the need for a theory that could go beyond Newton's limitations emerged. This is the point where physics stands at the crossroads between the classical and the modern. Here is where Einstein's theory of relativity would begin to challenge everything that was believed about gravity. But before delving into that, it is essential to understand how deeply Newtonian views had impacted science. Classical physics not only dealt with gravity, but also influenced other areas. From engineering to astronomy, Newton's laws provided a framework for understanding the universe. However, despite its success, scientists began to realize that there was more at stake. Gravity, while fundamental, was just one piece of the larger puzzle that is physics. Have you ever wondered why, despite all the advancements, gravity remains a topic of study? The answer lies in its inherent complexity. Although Newton provided an effective model, the nature of gravity is much more subtle than it appears. Each new observation, each new experiment opens the door to new questions and mysteries. The limitations of Newtonian physics remind us that scientific knowledge is a constantly evolving journey. As scientists face new challenges, they are driven to seek deeper answers. Gravity is not just a physical phenomenon, it is also a symbol of human curiosity and our desire to understand the universe. Thus, as we delve into the vast ocean of scientific knowledge, gravity presents itself as a beacon guiding explorers of the cosmos. While classical physics has provided valuable tools, the journey toward a complete understanding of gravity is just beginning. The questions that arise from our explorations propel us forward, reminding us that the pursuit of knowledge is, in itself, a powerful force that draws us toward the unknown. Gravity, that force that keeps us on Earth and makes apples fall from trees, transforms into a much deeper concept when we delve into Albert Einstein's theory of general relativity. But what did Einstein do to change our understanding of gravity? The answer goes beyond simply describing it as a force. It involves how it interacts with space and time. In classical physics, gravity was seen as a force that attracted objects to each other. But Einstein, in 1915, proposed a revolutionary idea. Gravity is not a force in the traditional sense, but a curvature of space-time. Can you imagine a trampoline? If you place a bowling ball in the center, the fabric deforms. Now, if you roll a marble near the ball, it will start to orbit around the ball due to the curvature created. Thus, Einstein shows us that massive objects like planets and stars warp the fabric of space-time. And it is this curvature that causes what we call gravity. Curiosity is a powerful engine. Why, if gravity is a curvature, do we not feel it differently all over Earth? This is where the concept that space and time are intertwined comes into play. Earth, while rotating and orbiting the Sun, creates an effect that keeps our feet firmly planted on the ground. But what would happen if we could travel to a black hole where gravity is extremely intense? The curvature of space-time would be so pronounced that time itself would slow down. Imagine experiencing a day in a black hole and coming out only to discover that 1,000 years have passed on Earth. Often people think that gravity acts uniformly throughout the universe, but the reality is that it varies. Einstein teaches us that gravity not only affects objects but also light. This is called gravitational lensing. And it's as if gravity can bend light around it, so when we observe a distant object in the universe, what we see may be distorted by the presence of other masses. In a sense, gravity becomes a lens through which we can observe the cosmos. Einstein's theory not only explains how gravity behaves, but also leads us to more intriguing questions. Can gravity affect light in such a way that we could use it to detect the presence of invisible objects? The answer is yes. This has allowed astronomers to discover galaxies and clusters of galaxies that would otherwise have remained hidden. Over time, general relativity has been tested through numerous experiments. For example, the famous solar eclipse experiment of 1919 demonstrated that light from stars bends when passing near the Sun, just as Einstein had predicted. This was a turning point in the acceptance of his theory and marked the beginning of a new era in physics. But how does this translate into our daily lives? Relativity is not just an abstract concept. The technology we use today, such as the global positioning system, relies on relativity. Satellites orbiting Earth must account for the effects of gravity and time dilation to provide accurate data. Without Einstein's understanding of gravity, our GPS system would be inaccurate and unreliable. General relativity also leads us to reflect on the universe on a much larger scale. It helps us understand cosmic phenomena such as the expansion of the universe and the existence of black holes. What mysteries lie behind them? Gravity plays a crucial role in their formation and behavior, prompting us to question their very nature. Einstein's journey through gravity is fascinating, but it doesn't end here. As scientists continue to explore the depths of space and time, new questions arise. What about quantum gravity, a theory that attempts to unite general relativity with quantum mechanics? This is a growing field of study that could change our understanding of gravity once again. The impact of Einstein's relativity on physics cannot be underestimated. It has opened the door to a range of new questions and theories that challenge our understanding of the universe. Gravity, in its essence, becomes a link between what we consider the everyday world and the mysteries of the cosmos. Reflecting on all this, it is astonishing to think about how a simple idea about the falling of an apple led to uncovering the secrets of the universe. Human curiosity, combined with the brilliance of minds like Einstein's, has allowed us to take giant steps toward a deeper understanding of gravity and, by extension, of ourselves and the place we occupy in the vast universe. The quest for knowledge never ends, and each answer generates new questions, inviting us to keep exploring and learning. Gravity is a phenomenon that constantly surrounds us, but have you ever thought about how it affects not only falling objects, but everything we know in the universe? It's fascinating to think that gravity is not just a force that keeps us on the ground, but it is also the reason why planets orbit around the sun and galaxies form and evolve. But how is it possible that something so invisible can have such a profound impact on the structure of space and time? Gravity, at its essence, can be visualized as a kind of fabric that stretches across the universe. When you place a heavy ball on a trampoline, the fabric deforms, creating a dip. This is a simple way to understand how gravity curves the space around it. The more massive an object is, the deeper the dip it creates. So when a smaller body, like a marble, rolls near that dip, it is drawn toward the larger object. In this case, the marble represents a planet, and the heavy ball represents the sun. Let's think about time for a moment. Did you know that gravity also affects how we perceive time? Imagine you have two clocks, one on the surface of the Earth and another on a satellite orbiting thousands of kilometers high. Although both clocks start at the same time, the clock on the satellite will show a slightly different time when it returns. This phenomenon is known as gravitational time dilation. In other words, time passes more slowly in the presence of a strong gravitational field, like that of the Earth compared to a place where gravity is weaker. It's as if gravity has its own clock. Now let's talk about how gravity not only affects the objects we see, but also light. Have you ever wondered why we see stars that are far away in the universe? The reason is that gravity can even bend light. When light from a star passes near a massive object like a galaxy, it curves, allowing us to see stars that would otherwise be hidden. This phenomenon is called gravitational lensing and is one of the ways astronomers can study the universe. Gravity also plays a crucial role in the formation of structures in the cosmos. From the formation of stars in nebulae to the creation of galaxy clusters, gravity is the force that binds everything together. As gas and dust in space accumulate due to gravity, they begin to collapse and form stars. Without this force, the universe would be a completely different place, lacking the beauty and complexity we know. But what happens when gravity becomes extreme? Let's talk about black holes. These are regions of space where gravity is so intense that nothing, not even light, can escape. The idea of a black hole may seem like something out of a science fiction movie, but they are very real. When a massive star runs out of fuel, it collapses under its own gravity, creating a black hole. This process is one of the most dramatic events in the universe and demonstrates how gravity can transform everything in its path. Throughout history, scientists have explored gravity from different perspectives. However, Einstein's theory of general relativity was a game changer. He proposed that gravity is not just a force, but a curvature of space-time. This meant that objects do not attract each other through an invisible force, but rather move along the curves in space-time. This idea revolutionized our understanding of gravity and opened new doors to scientific inquiry. Gravity also has fascinating implications in cosmology. For example, the expansion of the universe is affected by gravity. Initially, it was thought that gravity would be enough to slow down the expansion of the universe. But to the surprise of scientists, it was discovered that this expansion is accelerating. This is where the enigmatic dark energy comes into play, working against gravity and causing the universe to expand more rapidly. Can you imagine a universe where gravity did not exist? It would be total chaos where galaxies would disperse and there would be no structures as we know them. Gravity also helps us understand the possibility of life on other planets. The conditions on a planet, such as its gravity, are fundamental in determining whether it can support life. A planet with gravity similar to that of Earth could have liquid water, a suitable atmosphere, and potentially life. In contrast, a planet with very low gravity might not retain an atmosphere, making it inhospitable. So gravity is not just a scientific curiosity, but a key factor in the search for life beyond our planet. Finally, reflecting on gravity, it is evident that this force is much more than a simple attraction between objects. It is an integral part of the structure of the cosmos, affecting everything from the formation of stars to the ultimate fate of the universe. It invites us to explore more and question how the universe works. Gravity connects us in ways we may never have imagined, and each discovery about it brings us a little closer to understanding the great mystery of existence. So the next time you look up at the starry sky, remember that gravity is at the heart of every star, every planet, and every galaxy, weaving an incredible and complex tapestry that defines our reality. Gravity is a phenomenon that has fascinated humanity since time immemorial, but how can we be so sure it exists? Throughout history, scientists have conducted ingenious experiments to understand how gravity works and validate the theories surrounding it. Today we will explore some of those key experiments that not only confirmed the existence of gravity, but also revolutionized our way of seeing the universe. Let's start with a classic, Galileo's experiment and his famous inclination from the Leaning Tower of Pisa. It is said that he dropped two spheres of different sizes and weights at the same time. What do you think happened? Did the heavier one fall faster? To the surprise of many, both spheres touched the ground at the same time. This simple experiment demonstrated that, in the absence of air resistance, all objects fall at the same speed regardless of their weight. This was a significant blow to the Aristotelian notion that heavier objects fall faster. Following in Galileo's footsteps, a man named Newton wondered why apples fall from trees. Why don't they fly up into the sky? This curiosity led him to formulate the law of universal gravitation, but how could he prove his theory? Newton realized he needed to observe the motion of celestial bodies. So with his telescope, he studied the orbit of the moon and the planets. And what did he find? That the same force that makes apples fall also keeps the moon in its orbit. This discovery was a milestone that connected what we observe on Earth with what happens in the vastness of space. Now let's move to the 19th century, where a scientist named Cavendish conducted an experiment that measured gravity directly. Using an ingenious device, he measured the attraction between two lead masses. Did you know that this experiment not only confirmed Newton's law, but also allowed for the calculation of the Earth's density? Through a thread and a balance, Cavendish showed that gravity was not just a theory, but a force that could be measured and quantified. In the 1960s, a team of scientists conducted an even more intriguing experiment. The free fall of a sphere in a vacuum. Imagine an environment where there is no air, where resistance plays no role. When releasing a sphere and a lighter object, what do you think will happen? Both fell to the ground at the same time, reaffirming the idea that gravity acts uniformly on all objects regardless of their differences. Another experiment worth mentioning is the oscillation of pendulums. By observing a pendulum, one can notice that its movement is constant regardless of its mass. But what is the secret behind this movement? By measuring the time it takes for a pendulum to return to its initial position, scientists were able to learn more about the acceleration due to gravity. This simple yet effective experiment shows us how gravity affects time and motion. In the realm of modern physics, the drop tower experiment conducted in microgravity laboratories has opened new doors. By dropping objects in a free-fall tower, scientists can study how they behave without the influence of gravity. This experiment has been fundamental in understanding how forces work in space and how objects behave under extreme conditions. And we cannot forget the exciting discovery of gravitational waves. When two black holes collide, they generate waves that travel through space. Did you know that these waves were predicted by Einstein over a century ago? However, it wasn't until 2015 that they were first detected. With this detection, scientists have been able to further validate the theory of relativity and our understanding of gravity. The fall of objects on different planets has also been the subject of numerous experiments. Imagine trying to conduct a gravity experiment on Mars, where gravity is only 1/3 that of Earth. Scientists have sent missions to measure the fall of objects and study how gravity on other planets affects their movements. These experiments not only expand our knowledge about gravity, but are also crucial for the future of space exploration. And of course, the gravity experiment in space, where astronauts on the International Space Station experience a state of microgravity. Have you ever seen videos of astronauts floating? This unique experience is not only fascinating, but also helps scientists understand how gravity affects humans and other organisms under reduced gravity conditions. Each of these experiments has been a building block in constructing our understanding of gravity. Through curiosity and observation, we have unraveled many of the mysteries surrounding this fundamental force. Gravity is not just a force that keeps us on Earth, it is also the thread that connects planets, stars, and galaxies in the vast fabric of the universe. Science often relies on repetition and verification. Each experiment, from the simplest to the most complex, has helped cement our understanding of gravity. As we continue to explore and conduct new experiments, human curiosity will keep driving us to unravel the secrets of the universe, reminding us that although we have come a long way, there is still much to discover about this incredible force that surrounds us. The story of gravity is ultimately a story of exploration, discovery, and an endless quest to understand our place in the cosmos. When we look at the sky, we find ourselves surrounded by a vast and mysterious solar system governed by a fundamental force, gravity. But did you know that this force not only keeps our planet in orbit around the Sun, but also influences the dance of all celestial bodies, from gas giants to small asteroids? Gravity is the force that binds them together and gives them shape. In this section, we will dive into the crucial role that gravity plays in our solar system and discover why it is so fascinating. To begin with, let's consider Earth. Our planet is not just a home, but a huge magnet that pulls objects toward its center. This is what we feel as weight. But what would happen if we moved a little further away? What if we traveled to the moon? The gravity there is only 1/6 of what we experience here. This means that if you weigh 60 kilograms on Earth, on the moon you would weigh only 10. Can you imagine what that would do to your ability to jump? Gravity is the reason why the moon orbits our planet and does not drift away into space. Planets like Earth are in constant motion, but they are not alone. Each one orbits a star, and in our case, that star is the Sun. Why don't they escape their orbit? The answer lies in gravity. The Sun, being a massive body, has such an intense gravitational force that it keeps all the planets in their paths. It's as if the Sun is dancing with each of them, pulling them with an invisible force that keeps them in place. But it's not just the planets that are affected by this force. The moons, which orbit the planets, also feel the gravitational pull. For example, Jupiter's moon, Europa, one of the most fascinating moons, is subject to the gravitational forces of its giant parent and other bodies in its vicinity. This interaction can cause its surface to stir, which could be key to understanding the possibility of life beneath its ice. Now let's talk about asteroids. These small rocky bodies that orbit between Mars and Jupiter are also part of this grand theatre. The gravity of nearby planets can alter their trajectories, pushing them back and forth and even sending them inward into the solar system. In a universe where everything is in constant motion, gravity acts as a director, orchestrating the paths of these objects. Gravity is also behind impressive phenomena like tides. When the moon passes close to Earth, its gravity pulls on the ocean waters, creating an effect that we can see in the rise and fall of sea levels. This is not just a beautiful natural spectacle, but it also has a profound impact on marine life and coastal ecosystems. As we move away from the Sun, gravity continues to play a crucial role. At the edge of the solar system, we find Pluto and other dwarf planets. Although their gravity is much weaker than that of the giant planets, they are still capable of keeping their own moons in orbit, demonstrating that even smaller bodies have a role in this grand cosmic symphony. And we cannot forget comets, those travelers of space that come from the far reaches of the solar system. As they approach the sun, the gravity of this giant pulls them in and their nucleus heats up, releasing gases and dust, creating those beautiful tails that we all admire. Gravity, then, is not just a force of attraction, but also a transformative force that shapes and gives life to comets. The solar system is also full of mysteries. For example, there are certain objects that seem to be in orbit but do not fit into our traditional understanding. These are the so-called trans-Neptunian objects, which are found beyond Neptune. Their gravity interacts with that of other bodies, creating orbital patterns that we do not yet fully understand. But what about gravitation between solar systems? The stars in our galaxy, the Milky Way, are also bound by this same force. Each star, with its own gravity, affects nearby stars, creating a delicate balance in which each celestial body has its place. And as we venture into the universe, gravity remains the force that shapes galaxies, grouping them together and keeping them united. Looking to the future, gravity also poses intriguing questions about space exploration. Every mission we send into space, from rovers on Mars to satellites observing distant planets, must take gravity into account. The way we land on other celestial bodies and how we navigate between them depends on this fundamental force. Gravity, therefore, is much more than a simple attraction between masses. It is a force that shapes our solar system, orchestrating the dance of planets, moons, asteroids, and comets. Without it, our universe would be a very different place, a chaos in which nothing would have its place. In the end, understanding gravity is understanding one of the most important keys to unlocking the secrets of the cosmos. Who knows what else we will discover about this fascinating force in the future? Today we will explore one of the most fascinating phenomena in the universe: black holes. These mysterious entities have captured the imagination of scientists and enthusiasts alike. But what exactly are black holes and how do they form? To understand this, we must first think about what happens when a massive star exhausts its fuel. Imagine a large ball of gas and fire shining brightly in space. When this star runs out of energy, its core collapses under its own gravity, creating a phenomenon that challenges our understanding. Gravity, which normally keeps stars in balance, becomes the protagonist of this story. As the star collapses, gravity intensifies and the resulting object becomes so dense that not even light can escape its pull. This is how a black hole is born, a point in space where gravity is so strong that nothing can escape its embrace. But why are these holes so important in the cosmos? Black holes are not just a whim of nature. They are fundamental to understanding the structure of the universe. For example, it is believed that at the heart of every galaxy lies a supermassive black hole. Did you know that our own galaxy, the Milky Way, has one? It is called Sagittarius A*, and its mass is equivalent to millions of times that of the Sun. This black hole not only affects the stars that orbit around it, but also influences the formation and evolution of the galaxy itself. Now, if black holes are so powerful, why don't we see them with the naked eye? The answer lies in their nature. Being so dense, they do not emit visible light, but that doesn't mean we can't detect them. Astronomers have developed clever techniques to observe their influence. For example, they can observe how stars near a black hole move erratically, as if being pulled by an invisible force. It's like trying to see a magnet hidden inside a box. You can observe how it attracts objects around it, even though you can't see it directly. Black holes also have a mysterious ability. They can devour matter. When a star or any other object gets close enough, it enters what is called the event horizon, which is the point of no return. Imagine approaching a massive whirlpool in water. If you cross the edge, you won't be able to escape. Similarly, once something crosses the event horizon of a black hole, it is lost forever. But what happens to the matter that enters? Is it destroyed or transformed? Scientists are exploring this question. Some believe that matter is disintegrated into a torrent of energy, while others propose that there might be a form of storage of information inside the black hole. This idea has led to exciting debates about the nature of information and quantum physics. Could it be that black holes contain secrets of the universe that we have yet to unravel? Moreover, black holes are not static. They can merge with each other, creating even larger black holes. When this happens, they generate a gravitational wave, a kind of wave in space-time that can be detected. This discovery has opened a new window to astronomy, allowing us to hear the echoes of distant cosmic events, as if the universe were whispering its secrets through these waves. But what does the existence of black holes imply for our understanding of time and space? In their proximity, time behaves strangely. Imagine you are near a black hole where time slows down compared to the outside. This means that if you were on one side and your friend in another distant place, they could experience time completely differently. This is a fascinating aspect of Einstein's relativity, which shows how gravity can distort our perception of time. There is also an intriguing concept related to black holes, the information paradox. If the matter that falls into a black hole is destroyed, what happens to the information it contained? This question has challenged physicists for decades, leading them to rethink fundamental concepts about the nature of the universe. Could it be that black holes are not as definitive as we think? Perhaps instead of destroying information, they transform it in some way. The search for answers about black holes is an exciting journey that is constantly evolving. Scientists continue to develop theories and conduct experiments to better understand how they work and what their role is in the cosmos. Each new discovery brings us a little closer to unraveling the secrets of these enigmatic phenomena. As we gaze at the starry sky, we may wonder, how many black holes are there in our galaxy? The answer is astonishingly high. It is estimated that there could be millions of them, most invisible to us. However, their influence is felt in the dance of the stars and in the structure of our galaxy. Perhaps when we look at the stars, we are also looking into the heart of a black hole. Black holes are undoubtedly one of the wonders of the universe. They challenge us to think about the nature of reality, gravity, and time. As we continue to explore the cosmos, each new finding about these mysterious objects brings us closer to a better understanding of our place in the vast universe. So the next time you look up at the sky, remember that, although we cannot see them, black holes are there, waiting to be discovered, like the pages of an ancient book that we have yet to open. Gravity is an omnipresent force that influences every corner of the universe, but have you ever stopped to think about how this force affects galaxies? Gravity is not only responsible for keeping planets in orbit around stars, but it also plays a crucial role in the formation and evolution of galaxies. Imagine that each galaxy is like a huge cosmic garden where stars are the flowers that grow and gravity is the gardener that organizes and maintains the balance. When observing the vast universe, it is easy to see how gravity acts as a common thread that connects everything. Galaxies, composed of billions of stars, are formed by gravitational attraction. But how do these galaxies originate? At the beginning of the universe, after the Big Bang, there was a mix of particles and energy. Over time, small fluctuations in the density of this matter began to attract more matter through gravity. Like a magnet attracting iron filings, gravity started to gather particles, forming the first stars and eventually the galaxies we know today. Galaxies are not static entities, they are in constant motion and evolution. But what determines the shape of a galaxy? Gravity is the architect behind this structure. For example, spiral galaxies like the Milky Way have arms that extend due to rotation. Gravity keeps the stars in their orbits, allowing the galaxy to have that distinctive shape. On the other hand, elliptical galaxies have a rounder and smoother shape, resulting from gravitational interactions that have merged several smaller galaxies over billions of years. It is fascinating to think that gravity not only affects the shape of galaxies, but also their fate. Galaxies can collide and merge, a process that can take billions of years. This type of collision is like two rivers meeting and flowing together, creating new currents. When two galaxies collide, gravity plays a fundamental role in redistributing stars and gas, often leading to the formation of new stars amid the chaos. Thus, gravity becomes a driving force of change and renewal in the universe. However, not all gravitational interactions are harmonious. Some galaxies experience a phenomenon known as gravitational interaction, which can lead to the formation of supermassive black holes at their centers. What happens when two galaxies get too close? Gravity can tear apart their structures, causing material to accumulate in the center and in some cases form a black hole. This black hole in turn can begin to consume matter from its surroundings, creating a feeding cycle that has a profound impact on the galaxy itself. In the context of the expansion of the universe, gravity also has an intriguing function. As the universe expands, galaxies move away from each other. But what would happen if gravity were strong enough to slow down this expansion? Gravity acts as an attractive force that could, in theory, stop the expansion and begin a cycle of contraction. However, current observations suggest that the expansion of the universe is accelerating, a phenomenon that has led to the introduction of concepts like dark energy, a mysterious force that counteracts gravity. Studies on how gravity affects galaxies are not limited to observation alone. Astronomers use computer simulations to model the evolution of galaxies, trying to better understand the complex processes that occur in the cosmos. These simulations allow scientists to explore scenarios that cannot be directly observed, providing deeper insight into how gravity influences the formation and movement of galaxies. As we look to the future, understanding gravity and its relationship with galaxies remains an active area of research. With the advent of new telescopes and advanced technologies, such as the James Webb Space Telescope, scientists hope to obtain more detailed images of distant galaxies and how they have evolved over time. This new information could unveil secrets about the history of the universe and its large-scale structure. The quest to understand gravity and its impact on galaxies leads us to deeper questions about the universe. Are there more galaxies than we have observed? How does gravity affect the formation of life in those distant corners of the cosmos? Each discovery opens a new chapter in our cosmic history, and gravity remains a central theme in this narrative. The beauty of the universe lies in its complexity and in the interactions that occur at all levels. Gravity, although often considered a simple and familiar force, is actually a profound and enigmatic phenomenon that helps us understand the vast fabric of the cosmos. From the formation of galaxies to their evolution, gravity offers us a window into the mysteries of the universe, reminding us that, although we are small compared to the vastness, we are intrinsically connected to everything around us. Gravity is a fascinating phenomenon that not only keeps our feet on the ground, but also plays a fundamental role in the structure and evolution of the universe. But what if I told you that gravity is related to one of the most mysterious forces in the cosmos? Let's talk about dark energy, that enigmatic force that seems to be accelerating the expansion of the universe. Imagine a balloon being inflated. At first, when the balloon is small, the parts of its surface are quite close together. But as air enters and the balloon expands, those parts move apart. This is a good example of how the universe is expanding. However, what's surprising is that this expansion is not only happening, but is accelerating. Why? This is where dark energy comes into play. Dark energy represents about 70% of the total content of the universe, but what exactly is it? It's like a kind of force that pushes galaxies away from each other. But how does this relate to gravity? To understand this, it's crucial to remember that gravity is an attractive force. Think about how Earth's gravity keeps us firmly anchored to the ground. However, dark energy seems to be in conflict with gravity, acting as a push that counteracts gravitational attraction. If gravity is like a magnet that pulls objects together, dark energy could be compared to a leaf blower that pushes those same leaves in opposite directions. This tug-of-war between gravity and dark energy shapes the structure of the universe and its evolution. But what if gravity were stronger? Could dark energy be overcome? These are questions that scientists are constantly asking. In the quest for answers, astrophysicists have made observations of supernovae, which are explosions of massive stars. These explosions are so bright that they can be seen from incredible distances. By studying the light from these supernovae, scientists have been able to measure the rate of the universe's expansion. Surprisingly, they realized that not only was it expanding, but it was doing so faster than expected. This led to the conclusion that something must be pushing the universe outward, and that something is what we call dark energy. But the story doesn't end there. Dark energy could also have implications for the ultimate fate of the universe. If it continues to accelerate the expansion, there may come a time when galaxies drift so far apart that they become invisible to each other. Imagine a vast ocean of darkness where stars and galaxies are so distant that we can't see them. This is a possible future for the universe, one that could be dictated by dark energy. The relationship between gravity and dark energy is a puzzle that we have yet to fully solve. Some scientists believe that gravity could be weaker on cosmological scales due to the influence of dark energy. Other theories suggest that we might be witnessing a manifestation of new physics, something we have not fully understood until now. And here arises an intriguing question. Could there be other forms of dark energy that we have yet to discover? As telescopes become more advanced and technologies improve, scientists are on a constant quest to unravel these mysteries. The future of research on gravity and dark energy could open new frontiers in our understanding of the universe. Thinking about gravity and dark energy makes us reflect on the very nature of reality. If gravity is a force that keeps us together, what does that mean in an expanding universe? Are we destined to stay together in this vast cosmos? Or will we drift apart to become lonely islands of matter? Every new piece of information we gain about dark energy and its relationship with gravity brings us closer to an answer. Human curiosity is a powerful engine, and each discovery invites us to ask new questions. What lies beyond what we know? What secrets does the universe still hold? The pursuit of knowledge is endless, and gravity, along with dark energy, reminds us that there will always be more to discover. From Earth to the farthest reaches of the universe, every step we take on this journey brings us closer to a greater understanding of our reality. So the next time you look up at the starry sky, remember that you're not just seeing stars, but also a constantly changing universe where gravity and dark energy play a crucial role. What other mysteries await us in the vastness of the cosmos? The answer is out there, waiting to be discovered. Quantum gravity is a topic that sparks the curiosity of many, and rightly so. How can we reconcile the enormous force that attracts planets and stars with the strange and fascinating world of subatomic particles? This dilemma has led physicists from around the world to seek answers that could change our understanding of the universe. Gravity, as we know it, is a force that acts between masses, but quantum mechanics operates in a realm where the rules are different. Imagine a world where particles are like players in a soccer match, but instead of following clear rules, they sometimes act in completely unpredictable ways. How can we unite this quantum chaos with the stability of gravity that keeps our feet on the ground? This is the essence of the challenge of quantum gravity. A key concept in this search is the idea that gravity might not just be a force, but something more fundamental. In Newton's classical physics, we understand gravity as an attraction between masses. However, in the quantum world, scientists are exploring whether gravity could be the result of the very geometry of space-time. Imagine that space and time are a vast spider web, in which massive objects create dips that attract other objects like marbles rolling across the net. This approach suggests that gravity may be more related to the shape of the universe than to a force acting at a distance. One of the most well-known attempts to unify gravity with quantum mechanics is string theory. This idea proposes that subatomic particles are not points, but rather vibrating strings. Depending on how they vibrate, these strings can manifest as different particles. What if gravity could also be explained through these strings? This would not only offer a new way to understand gravity, but could also help explain other fundamental forces of nature. However, so far, string theory remains a highly theoretical concept without definitive experimental evidence. Another interesting avenue is emergent gravity. In this approach, it is suggested that gravity is not a fundamental property, but emerges from more basic interactions between particles. as if gravity were a phenomenon that appears when a large number of particles behave in a certain way, similar to how temperature feels tangible, even though it is the result of the movement of individual particles. This concept may seem strange, but it is an example of how scientists are thinking outside traditional boundaries to solve the puzzle of gravity. And here arises an intriguing question. How can we measure gravity in the quantum context? Experiments designed to explore quantum gravity are often complex and require advanced technology. One of the most promising methods is the use of quantum interferometry, which allows scientists to observe how particles behave under the influence of gravity. Through these experiments, it is hoped to gain insights into the nature of gravity at very small scales. Additionally, other innovative methods are being considered, such as studying gravity in extremely small systems where quantum interactions are more pronounced. Imagine a laboratory where atoms and molecules are manipulated with the precision of a surgeon, searching for patterns that could reveal the secrets of quantum gravity. These experiments are not only exciting, but also have the potential to open new doors in our understanding of the universe. As research progresses, ethical and philosophical questions also arise. If one day we succeed in unifying gravity with quantum mechanics, how will that change our view of the universe? The idea that everything is interconnected through forces and particles can be both liberating and unsettling. It leads us to question our relationship with the cosmos and our own existence. Quantum gravity is not just a challenge for theoretical physicists, it also raises questions about the future of technology. Could understanding gravity at the quantum level lead us to new innovations, perhaps even to the creation of devices that harness this force in ways we have yet to imagine? Just as electricity transforms society, quantum gravity could open a new chapter in the history of science and technology. The future of quantum gravity is exciting and full of possibilities as scientists continue to explore this vast unknown territory. Each advance, each new experiment brings us a little closer to unraveling the mysteries surrounding this fundamental force. Gravity, in its purest form, remains an enigma, but the quest for answers is what drives humanity forward. In summary, quantum gravity represents the crossroads between two of the most powerful theories in physics. The search for a unified theory that explains gravity in quantum terms is not only a scientific challenge, but also a journey that invites us to reflect on our understanding of the universe. Who knows what discoveries await us on the horizon? The exploration of quantum gravity could be the first step toward a new era of knowledge, where science and human curiosity intertwine in a journey into the unknown. Quantum gravity is a fascinating field of research that seeks to unravel one of the greatest mysteries of modern physics. How is it possible that two theories as successful as quantum mechanics and general relativity, which describe the universe at very different scales, do not get along? Imagine you have two friends who, although they are great at what they do, cannot stand each other. That is the situation between gravity and quantum mechanics. While gravity, in the context of relativity, describes how massive objects behave in space, quantum mechanics focuses on the world of the extremely small, where subatomic particles dance in a game of probabilities. In this sense, quantum gravity attempts to find common ground. But how can something as large as a black hole be combined with something as small as an electron? This is where the imagination of scientists comes into play. Some propose that gravity could be a manifestation of more fundamental structures, something like a fabric that composes the universe. But how can something so ethereal and abstract be measured? One of the most intriguing approaches is string theory. Imagine that instead of point particles, everything in the universe is made of tiny vibrating strings. Each type of particle corresponds to a different vibration of these strings. Thus, gravity could arise from the way these strings interact. But does this mean we live in a universe of multiple dimensions? That is another question physicists ask, as string theory suggests that there are additional dimensions beyond the three we know. Another approach is loop quantum gravity, which visualizes space and time as a network of small, discrete units like a chessboard where each square represents a portion of space-time. In this view, gravity is not a continuous force as we understand it, but becomes something granular. But how could we verify if this network actually exists? The answer lies in experiments. Experiments attempting to measure gravity at quantum scales are quite a challenge. For example, scientists have been trying to detect gravitational waves, which are small disturbances in space-time caused by massive events like the merging of black holes. Detecting these waves is like trying to hear a whisper in the middle of a crowd. It is a meticulous job that requires very advanced technology. One of the most ambitious projects in this field is the LIGO experiment, which has successfully detected gravitational waves. This not only validates Einstein's theory, but also opens the door to new questions. If we can capture these waves, will we also someday be able to observe quantum gravity in action? The answer lies in the future of research and technology, but it's not just about detecting phenomena. There are experiments that seek to create conditions where quantum gravity can manifest. Some researchers are using ultra-cold atoms to observe how they behave in situations that challenge our current notions of gravity. These experiments are like small laboratories of the cosmos in miniature, where scientists can play with the rules of the universe. And what about the possibility that quantum gravity has implications for our understanding of the universe? Imagine that gravity, as we know it, is just the tip of the iceberg. If we manage to unify gravity with quantum mechanics, we could unveil secrets about the creation of the universe, or even about what lies beyond it. Of course, quantum gravity also raises many philosophical questions. If space and time are discrete, does this mean that reality is fundamentally different from what we perceive? Are we trapped in an illusion created by our own sensory limitations? These questions may sound abstract, but they are the engine that drives human curiosity. Some scientists even suggest that understanding quantum gravity could bring us closer to answering questions about the nature of consciousness and existence itself. Is it possible that by studying gravity at quantum levels, we are also exploring the limits of the human mind? This may seem like a leap, but science often intersects with philosophy in surprising ways. Meanwhile, the scientific community continues to advance. There are many projects underway around the world, from laboratory experiments to astronomical observations, all aimed at shedding light on this enigmatic intersection between gravity and quantum mechanics. The search for answers is intense and exciting, and each small finding is another step toward understanding one of the great mysteries of the universe. So the next time you think about gravity, remember that there is a world of discovery still waiting for us. Quantum gravity is not just a field of study, it is a window into new ways of seeing the universe, an invitation to question what we think we know and to explore the unknown. The story of gravity is far from over, and every day new pages are being written in this fascinating book of the cosmos. Gravity is a phenomenon that accompanies us at every moment of our lives, but what if I told you that not all gravitational forces are the same? On our own planet, gravity feels constant, but when we look at other celestial bodies, we discover a surprising variety. How does gravity vary on other planets? What effect does this have on life and the possibility of colonization? Let's delve into this fascinating topic. To begin with, let's think about Earth. Gravity here is what keeps us firmly grounded. If we jump, we know we will come back down. But what happens on other planets? Each one has a different size and mass, which means the gravitational force they exert also varies. For example, on Mars, which is smaller than Earth, gravity is about 38% of ours. Can you imagine being able to jump almost 3 times higher? It would certainly be a fun sight. Now, what about Jupiter? This gas giant has a mass more than 200 times that of Earth. The gravity on its surface is so intense that a human would weigh more than twice their usual weight. This would not only affect our ability to move, but would also have serious implications for health. Can you imagine living in an environment where every step you take requires double the effort? It would certainly be quite a challenge. But gravity doesn't just affect humans. Life as we know it has evolved in a specific gravitational context. On planets with different gravity, there could be different forms of life adapted to those conditions. Plants, for example, might grow in unusual ways. In a world with lower gravity, trees could reach incredible heights, as they wouldn't have to support the same weight in their trunks. What forms of life could exist in those distant worlds? Another fascinating aspect is how gravity influences water and other liquids. On a planet with lower gravity, water might flow differently. Oceans, lakes, and rivers would have unique characteristics. Imagine an ocean where instead of waves, there are gentle currents that move slowly, as if dancing to the rhythm of a soft melody. This could have a profound impact on climate and the development of life. Gravity also plays a crucial role in the formation of human colonies on other planets. If one day we decide to establish a base on Mars, what challenges would we face? The lower gravity could affect not only our physical health, but also how we build our homes and how we grow our food. An environment with different gravity would require innovations in technology and architectural design. And what about dwarf planets and asteroids? On smaller celestial bodies, gravity is so weak that they may not be able to retain an atmosphere. This means that in those places there could be no liquid water, a fundamental requirement for life as we know it. On an asteroid, you could jump and float as if you were in some kind of zero-gravity amusement park. But would it really be a habitable place? Moreover, gravity influences how planets rotate and orbit around the Sun. Each celestial body has its own gravitational history, which determines its trajectory and its relationship with other planets. The gravitational interaction between them can lead to the creation of rings, like those of Saturn, or even the formation of moons. Have you ever wondered what life would be like on a moon? Perhaps in the future we will discover human colonies on those worlds. Space missions have allowed scientists to study how gravity affects astronauts in space. On the International Space Station, astronauts live in a state of microgravity, which allows them to experience a sensation of weightlessness. This gives us clues about what life might be like on other planets and how we could adapt to those conditions. What would happen if humanity adapted to living in an environment with different gravity? The possibilities are endless. Finally, we cannot forget that studying gravity on other planets also helps us better understand our own home. By comparing Earth's gravity with that of other celestial bodies, scientists can learn more about the history and evolution of our planet. Each discovery brings us one step closer to unraveling the mysteries of the universe. In conclusion, gravity on other planets is a topic that not only sparks our curiosity, but also challenges us to imagine a future where humanity could live and thrive on different worlds. The variability of gravity can influence life, technology, and space exploration. As we explore the universe, each new discovery about gravity offers us a new perspective on our place in the cosmos. Who knows what surprises the future holds in the search for other habitable worlds? What are gravitational waves really, and why are they so important for understanding our universe? Imagine that space-time is like a large elastic surface. When you place a heavy object like a bowling ball on that surface, it creates a dent. Now, if you roll a marble near that dent, you'll see the marble move toward the bowling ball, not because there is a direct force between them, but because the elastic surface has been deformed. This is a key concept for understanding how gravitational waves function in the vast cosmos. Gravitational waves are disturbances in the fabric of space-time caused by the accelerated movements of very large masses, such as two black holes orbiting each other and eventually merging. This event is not trivial. It's like two gigantic whirlpools of water joining together in a cosmic ocean. The energy released during that merger creates waves that travel through the universe at the speed of light, allowing us for the first time to hear astronomical phenomena that we could only observe through light before. Did you know that the first detection of gravitational waves was announced in 2015? It was a historic moment, comparable to the discovery of radio or the use of the telescope. The LIGO collaboration, an experiment spanning 2 facilities in the United States, successfully captured these waves for the first time, thus confirming the predictions of Einstein's general theory of relativity. The excitement of the scientists at that moment was palpable, as they not only validated a theory that had been over a century old, but also opened a new window to explore the universe. The question that arises is, what can we learn from these waves? Gravitational waves offer us a new way to observe the universe, different from what light provides, while telescopes allow us to see objects that emit or reflect light. Gravitational waves tell us about events that are often hidden from our view. They narrate stories about black hole collisions, supernova explosions, and star formation, enabling us to explore phenomena that were previously invisible. Visualize this. When a massive star explodes in a supernova, it not only emits bright light, it also generates gravitational waves that propagate through space. If we had a microphone sensitive enough, we could hear the echo of that explosion thousands of light years away. This allows us to study the origin and evolution of stars in a way we never imagined possible. The impact of detecting gravitational waves goes beyond pure scientific curiosity. These waves provide a new tool for testing general relativity. When detected, scientists can compare theoretical predictions with reality, helping us refine our understanding of gravity. It's as if we have a new set of rules to understand physics, where each detection is a move that teaches us more about the universe. As technology advances, new observatories are expected to be developed that can capture gravitational waves of different frequencies. This means that in the future, we could learn about even more distant and energetic events. Imagine the possibility of hearing the songbook of the universe, where each event, each collision, becomes a note that forms part of a cosmic symphony. Of course, not everything is straightforward. Gravitational waves are incredibly weak and require extremely sensitive technology to be detected. Facilities like LIGO and its successor, the second-generation Gravitational Wave Observatory, are designed with millimeter precision to capture these tiny vibrations in space. It's a bit like trying to hear the whisper of a leaf falling in the middle of a storm. The detection of gravitational waves also opens up a range of questions. What other cosmic phenomena might be generating waves that we have yet to discover? What secrets does the universe hold in its darkest corners? These questions are the subject of active research in the scientific community, and each new detection promises to take us further in our understanding. A fascinating aspect of gravitational waves is their relationship with black holes. At the moment, two black holes merge, they release an immense amount of energy, equivalent to what could be generated by billions of suns in an instant. Each time a black hole merger is detected, we not only confirm the existence of these mysterious objects, but also delve into the study of the very nature of gravity, reflecting on the significance of all this. Gravitational waves are not just a new phenomenon to study. They allow us to connect with the universe in a completely new way. They show us that there are many more layers to what we perceive, inviting us to explore and question what we know. Thus, at a time when science is constantly evolving, gravitational waves represent an exciting path toward the future. They remind us that our universe is a dynamic and ever-changing place, full of surprises and wonders. We can't wait to see what else the cosmos will reveal to us as we learn to listen to its music. How would our lives be without gravity? It is such a commonplace concept that we often take it for granted. But have you ever thought about how the understanding of gravity has transformed modern technology? From the simple act of walking to the incredible precision of satellite navigation systems, gravity plays a crucial role in each of these advancements. Without it, our daily lives would be radically different. When we talk about GPS, most of us simply use it to get to a location. But did you know that the functioning of GPS depends on gravity? The satellites orbiting the Earth move at high speeds and at considerable altitudes. Due to gravity, they experience time dilation, a phenomenon that Einstein described in his theory of relativity. That's why the clocks on these satellites keep time differently than the ones we have on Earth. If we didn't take these effects into account, your GPS could lead you to the wrong place, and that could be very problematic. Satellite technology is not limited to navigation, it also plays a crucial role in meteorology. The images and data that satellites collect about the Earth's atmosphere depend on gravity to orbit in their precise trajectories. Without a clear understanding of how gravity works, we wouldn't be able to effectively predict storms, hurricanes, or climate changes. In this sense, gravity not only affects our lives but also helps us protect them. Smartphones, those devices we carry everywhere, also depend on gravity. Inside them, there are small accelerometers that detect the orientation of the device. Have you ever wondered how your phone knows whether to switch from vertical to horizontal when you rotate the screen? It all comes down to gravity and how these sensors perceive it. Without gravity, these devices couldn't function as they do today. Moreover, gravity influences how communication systems develop. Radio waves and other types of communication signals are affected by the Earth's gravity. For example, to transmit signals from a satellite to Earth, it is essential to understand how gravity affects the trajectory of those signals. Without this understanding, modern communications such as video calls or music streaming would be impossible. In the field of space exploration, gravity plays a fundamental role. When spacecraft are launched into space, they must leverage gravity to enter orbit. The famous gravity assist or slingshot is used to accelerate the spacecraft by utilizing the gravitational pull of other planets. This allows interplanetary missions to save fuel and time, taking human and robotic explorers further into the solar system. Medicine also benefits from our understanding of gravity. In hospitals, technologies like MRI rely on magnetic fields and gravitational forces. Researchers are constantly looking for ways to use gravity to improve diagnostics and treatments. Additionally, when astronauts spend time in space, their bodies undergo significant changes due to the lack of gravity, which helps us better understand human health. Another area where gravity has a significant impact is in sports. Coaches and athletes study how gravity affects physical performance, from how a soccer player kicks a ball to how a gymnast performs a jump. Gravity influences every movement. Understanding this force can help athletes optimize their performance and reduce the risk of injury. The entertainment industry also benefits from the understanding of gravity. In movies and video games, special effects depend on simulating gravity. From explosions to acrobatic jumps, each effect takes into account how an object would behave in a realistic gravitational environment. This allows for the creation of more immersive and exciting experiences. As we move into the future, research on gravity continues to evolve. Scientists are exploring new methods to measure gravity with greater precision. This could have applications in a variety of fields, from engineering to geology. Gravity not only helps us understand our world, but also provides us with tools to build a better future. The importance of gravity extends beyond science and technology. It also invites us to reflect on our place in the universe. The way we interact with this invisible force reminds us that we are part of a much larger system. Every time we feel the weight of our own bodies, we are connected to the fundamental laws that govern the cosmos. Gravity is more than just a simple attraction. It is an essential element in the very fabric of reality. From the technologies we use every day to the deeper questions about the universe, gravity remains a mystery that drives us to keep exploring. Undoubtedly, it is a fascinating journey that has only just begun, so the next time you feel heavy when getting out of bed, remember that it is gravity working on you, and that thanks to it, our modern life is possible. Gravity is one of those forces that, although invisible, has a monumental impact on our lives. Have you ever thought about how this fundamental force has been key to the development of life on Earth? Since the planet formed, gravity has been present, shaping not only the structure of the Earth, but also the course of evolution for all the species that have inhabited this world. When we talk about life, gravity plays a crucial role in aspects ranging from how plants grow to how organisms develop. Imagine a seed falling to the ground. Gravity not only pulls it toward the center of the Earth, but also influences its growth. This force determines the direction in which the root burrows into the soil and how the stem rises toward the sunlight. Without gravity, roots wouldn't know where to go and plants would simply float in the air. This would mean we wouldn't have the diversity of vegetation we see today. As life evolved, gravity also influenced how animals developed. Creatures that inhabited the oceans, like fish, had to adapt to water pressure and the force of gravity. But what about the animals that decided to leave the water and conquer the land? Gravity posed a completely new challenge for them. The bones and muscles of land animals had to evolve to support their own weight and move efficiently. Without gravity, the development of vertebrates on Earth would have been radically different. They might not even exist. Moving to the human sphere, gravity has influenced how our species has adapted to its environment. Humans have evolved to be bipeds, meaning we walk upright. This posture has not only allowed us to see farther and be more efficient in covering distances, but it has also been a response to gravity. By standing upright, our bones and joints have developed a structure that supports gravitational force, enabling us to move gracefully and agilely. Can you imagine what life would be like in an environment with different gravity? On the Moon, for example, gravity is only 1/6 of what we experience on Earth. This means that a jump that here might take you to the ground in an instant would allow you to float in the air for much longer on the Moon. If humans decided to settle on the Moon, their bodies would undergo significant changes. Lunar gravity could affect bone density and muscle mass, requiring people to adapt to a new lifestyle. Gravity is not only responsible for keeping us upright, but also regulates the water cycle and climate. Without it, water wouldn't stay in oceans, rivers, and lakes. This would mean we wouldn't have the fresh water that is vital for life. Gravity allows water to flow from one place to another, creating a cycle that is fundamental for all terrestrial ecosystems. The rains, rivers, and lakes we know are possible thanks to this force that pulls water toward the center of the Earth. In the realm of biology, gravity also plays a role in how our bodies use nutrients. Gravity influences blood circulation, as the heart must pump blood against gravitational force to reach all parts of our body. If you were in a microgravity environment like on a spacecraft, you would notice that your body wouldn't function the same way. Astronauts in space experience physical changes such as loss of muscle mass and bone density due to the lack of gravity. Gravity has also been a factor in space exploration. When scientists and astronauts think about establishing colonies on other planets, they must consider how gravity will affect human life. On Mars, for example, gravity is about 1/3 that of Earth. This could mean that humans would need to develop special technology and structures to adapt to this environment, ensuring they can live and thrive in a place where conditions are so different. Moreover, gravity plays a role in the search for extraterrestrial life. Scientists analyze how a planet's gravity can affect the possibility of liquid water existing, an essential ingredient for life as we know it. So when a new exoplanet is discovered, one of the first aspects studied is its gravity, as this can provide clues about whether it might harbor life. With all these influences, it is clear that gravity is not just a force that keeps us grounded. It is a fundamental element that has shaped the evolution of life on our planet, affecting how we interact with our environment. The way plants grow, how animals evolve, and how humans adapt to different conditions are all intrinsically linked to this invisible force. It is fascinating to think about how, in every corner of our world, gravity plays its role. From the movement of tides to the flight of birds, its influence is everywhere. Life, as we know it, is a testament to the incredible dance between gravity and evolution. Without this force, the history of life on Earth would be completely different, and perhaps we wouldn't even exist at all. Gravity, in its simplicity, is the thread that weaves together all life, connecting every living being in this vast universe. What do we really know about gravity? Often people think that gravity is just the reason objects fall to the ground, but what if I told you there's much more at stake? Many myths and misconceptions have arisen over the years about this fundamental phenomenon of the universe. Let's start to unravel some of them. First, let's talk about the idea that gravity is a phenomenon that only acts on Earth. While it is true that we feel its effect more intensely here, gravity is everywhere. From the moment you step out of your house, you are being pulled by Earth's gravity, but you are also influenced by the gravity of the Sun and other celestial bodies in the vast universe. Gravity knows no bounds. It extends throughout the cosmos, connecting everything that exists. Another common myth is that gravity is constant. Some people believe that the gravity we experience here on Earth is the same anywhere in the universe. However, this is not the case. Depending on the celestial body you are on, the gravitational force can vary. For example, on the Moon, gravity is only 1/6 of Earth's gravity. This means that if you weigh 60 kilograms on Earth, you would weigh only 10 on the Moon. Imagine what you could do with that light weight. Additionally, there is the misconception that larger objects have stronger gravity. While it is true that a massive planet has a greater gravitational pull than, say, a rock, gravity is not measured solely by size but also by density. A small but extremely dense object like a neutron star can exert immense gravity. This is a fascinating concept that reminds us that not everything that shines is gold, and gravity can be deceptive. Then there is the confusion between weight and mass. Many people use these terms interchangeably, but they are actually different. Mass is the amount of matter in an object and does not change, no matter where you are in the universe. In contrast, weight is the force that gravity exerts on that mass. Therefore, in an environment with less gravity, like the Moon, your weight would be less, even though your mass would remain the same. It's an interesting mental game. What about ideas about gravity in space? Many believe that there is no gravity in space. This is one of the most misguided notions. In reality, gravity is present in space. It is what keeps planets in orbit around the Sun and moons in orbit around planets. What astronauts experience on the International Space Station is a sensation of weightlessness, but this is because they are in a state of free fall. Not because gravity does not exist. Gravity is also mistakenly seen as a phenomenon that only affects large objects. The truth is that even molecules and atoms are influenced by gravity, although its effect is infinitesimal at that scale. Gravity continues to act on all things, big and small. This means that every atom in your body is being pulled by gravity, creating a universal connection that is astonishing. Let's also talk about the famous saying that what goes up must come down. While it is true that objects we throw into the air come back down, this is not an absolute rule. In space, objects can continue to move indefinitely if there are no forces to stop them. So, while on Earth they always return to us, in the vast universe the rules change and gravity plays a different role. A concept that is often misunderstood is gravity and speed. Some people think that the speed of an object can overcome gravity. However, in reality, gravity is always present, and what is really needed is enough energy to overcome it. This is what happens with rockets. They require a huge amount of energy to escape Earth's gravitational pull and reach space. The idea that gravity is simply a force is also a common mistake. Gravity is not just a force acting at a distance. In Einstein's general relativity, it is described as a curvature of space-time. This is a complex notion, but in simple terms, we can imagine that massive objects warp the fabric of space, creating a sort of dip that other objects feel as an attraction. So in a sense, gravity not only pulls us, it also shapes the space around us. What about gravity and myths about time? Some think that gravity affects time in peculiar ways. In reality, gravity can influence the perception of time. The stronger the gravitational field, the slower time passes. This is an idea that comes from general relativity and may sound like something out of a science fiction movie, but it has scientific basis. In fact, clocks on the surface of the Earth keep time differently than clocks that are in orbit, where gravity is weaker. Finally, have you ever heard that gravity can be cancelled? There are experiments and technologies that can create a state of weightlessness, but this does not mean that gravity has disappeared. We are simply creating conditions in which its effects are not perceived in the same way. It is a reminder that gravity is a constant that is always present even when we do not feel it. In summary, gravity is a topic full of myths and misunderstandings that invite us to question our perceptions and explore more deeply how the universe works. As we continue to investigate and learn about gravity, it is essential to demystify these misconceptions. The next time you think about gravity, remember that it is not just a force that keeps us on the ground, but a complex phenomenon that connects everything in the cosmos. What does the future hold in our quest to understand gravity? Gravity has been a mystery for centuries, and while we have made significant progress, there is still much ground to explore. Human curiosity is insatiable, and every time we unravel a secret of the universe, more questions arise that push us to continue investigating. Gravity, the force that keeps us anchored to the Earth, is just the tip of the iceberg in a depth of knowledge yet to be discovered. One of the most intriguing questions is, how can we unify gravity with the other fundamental forces of nature? Modern physics tells us that there are four forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. While the last three combine well within the framework of quantum mechanics, gravity seems out of place. Imagine a puzzle where one piece simply doesn't fit. Gravity behaves differently, leaving us with the conundrum of how to reconcile these forces. Scientists are working on theories like quantum gravity, which attempts to describe gravity in terms of quantum mechanics. But what does this really mean? To understand it, let's think about how gravity affects large objects like planets and stars, and how quantum mechanics describes subatomic particles. The key is to find a way for these two realities to communicate with each other. In this sense, quantum gravity is like a bridge connecting two worlds that, at first glance, seem incompatible. A promising approach is string theory. This theory suggests that instead of point-like particles, what really exists are vibrating strings. Each vibration of a string would correspond to a different particle. This approach not only offers a way to unify all forces, including gravity, but also suggests the existence of additional dimensions beyond those we can perceive. Imagine living in a world where there are more dimensions than the three we know, and how that could change our understanding of gravity. Moreover, there are ongoing experiments seeking to measure gravity at quantum scales. One of the most fascinating is the quantum interferometry experiment, which uses light to investigate how quantum effects can influence gravity. Through advanced techniques, scientists hope to observe how gravity affects particles in a quantum state. Could it be that gravity behaves differently at very small scales? This type of research could open new doors to understanding gravity. On the other hand, what about gravity on other planets and celestial bodies? Space exploration has allowed us to measure gravity in different contexts, from Mars to the gas giants. Each place has its own gravitational signature, and understanding these differences is not only fascinating but also crucial for future colonization or exploration missions. How will Martian gravity affect future human colonists? What challenges will it present in terms of health and development? And let's not forget the influence of gravity in extreme phenomena, such as black holes. As scientists study these cosmic mysteries, questions arise about how gravity can lead to situations that challenge our current understanding of time and space. Delving into the world of black holes, it becomes evident that gravity can create effects so intense that time itself behaves in strange ways. What secrets do these dark giants hold that could change our view of the universe? Meanwhile, gravity also plays a role in the expansion of the universe. Dark energy, that mysterious force that seems to be accelerating expansion, exists in a delicate balance with gravity. How can this opposing energy exist? And what does this mean for the future of the universe? Research on dark energy and its relationship with gravity is fundamental to understanding the evolution of the cosmos, and there is still much to learn. With each new discovery, scientists are driven to question existing theories and seek deeper answers. Gravity remains an enigma that raises more questions than answers, and it is precisely this that keeps the spark of scientific curiosity alive. What new theories will emerge in the next decade? What technological advancements will allow for a deeper understanding of this omnipresent force? As we continue to explore, it is essential to remember that gravity is not only a force that affects us physically, but also influences our philosophical understanding of the universe. Each discovery about gravity leads us to reflect on our place in the cosmos and our relationship with the forces that surround us. The search for truth in the nature of gravity is ultimately a quest for knowledge and understanding of ourselves. So, what does the future hold? Gravity will continue to be a fascinating topic of research filled with unanswered questions and opportunities for discovery. As science advances, we too must advance in our understanding, always keeping alive the curiosity that drives us to explore the unknown. Gravity connects us not only to the Earth but to the vast universe around us, and every step we take in its study is a step toward a greater understanding of our place in the cosmos. The adventure is just beginning. Gravity, that invisible force that keeps us anchored to the Earth, is much more than a simple attraction between objects. It is a thread that weaves through every corner of the universe, from the small stones on the ground to the colossal galaxies. Have you ever stopped to think about what life would be like without it? Gravity not only defines our environment but also plays a crucial role in the cosmic dance of celestial bodies. Without it, planets as we know them would not exist, nor the stars that light up our nights. Throughout history, humanity has sought to understand this fascinating force. From the ancient Greeks who speculated about the movement of the stars to the revolutionary discoveries of Isaac Newton and Albert Einstein, each advancement has been a step toward understanding a mystery that has captivated thinkers for centuries. Gravity has been and continues to be a topic of exploration and wonder. Isn't it amazing to think that a simple apple falling from a tree inspired profound reflections on the workings of the universe? Newton's law of universal gravitation, for example, established that all bodies attract each other. This idea transformed science and allowed us to predict the movement of planets with astonishing precision. But what happens when we delve into the world of extreme speeds and enormous masses? The answer came with Einstein's general theory of relativity, which showed us that gravity is not just a force but a curvature of space and time. Can you imagine a canvas that deforms when a heavy ball is placed in its center? That's how gravity acts on the fabric of the universe. The implications of this understanding are profound. The way gravity affects time is a concept that seems straight out of a science fiction novel, but it is reality. If you were to travel to a nearby star at the speed of light, you would experience time differently than those who remain on Earth. Isn't it incredible to think that gravity can even alter the way we live and experience time? The experiments that have validated these ideas are equally fascinating, from the famous Cavendish experiment, which allowed for precise measurement of gravity, to the recent detections of gravitational waves. Each discovery has brought humanity a step closer to unraveling the secrets of the universe. Who would have thought that ripples in space-time could be heard like melodies of the cosmos in our own solar system? Gravity acts as a conductor, organizing planets, moons, and asteroids into a celestial harmony. Without it, Earth could not maintain its orbit, nor could the moon dance in its eternal revolution. But what about black holes? These mysterious regions of space where gravity is so intense that nothing can escape represent one of the greatest enigmas of modern physics. What secrets do they hold within their dark embrace? Gravity does not only affect our small corner of the universe, it plays a fundamental role in the formation and evolution of galaxies, influencing how they group and develop over billions of years. Have you ever wondered how galaxies form and what role gravity plays in that process? It's as if the universe is woven with a network of forces that shape its structure. However, the story of gravity does not end here. Dark energy, that mysterious component that seems to accelerate the expansion of the universe, intertwines with our understanding of gravity. How can something so ethereal influence gravity and, in turn, the fate of the cosmos? This is a question that scientists are still trying to answer. As we explore gravity at the quantum level, we enter a territory filled with possibilities and challenges. The search for a theory that unifies gravity with quantum mechanics is one of the greatest challenges of modern physics. What discoveries await us on this journey into the unknown? Each experiment, from the simplest to the most complex, could offer us clues about how gravity truly works at the deepest level. Comparing gravity on other planets and celestial bodies opens a new horizon in our understanding. Imagine living in a place where gravity is much stronger or much weaker. How would that affect life? Would we be able to adapt? Gravity, in this sense, is a determining factor in the possibility of colonizing other worlds. Gravitational waves discovered in the last decade are a testament to the power of this force. Like ripples in a pond, these disturbances in space-time offer us a new way to observe the universe. What other secrets will they reveal to us in the future? Modern technology, driven by our understanding of gravity, has transformed the way we live. From GPS to satellite navigation, gravity is the compass that guides our way. Finally, gravity is more than just a simple physical force. It is an essential component in the development of life as we know it. Without it, Earth would not be the home we know. The existence of life on other planets could depend on gravity, leading us to reflect on our place in the vast universe. So as we look toward the stars, let us remember that gravity not only keeps us grounded, but also connects us to the immensity of the cosmos. In this journey of exploration, every question posed could open the door to new answers. And every answer could lead us to countless new questions. Gravity, in its essence, is a reminder of how wonderful and mysterious our universe is.